Okay, antiderivatives. Big deal. So we started chapter 6 before we went on break, which means we started doing integration. Antiderivatives will be a huge part of integration. We will be using it pretty much for most of the times you do integrals by hand. Most of the time you do integration by hand, you will be using antiderivatives. They're a big deal. Okay. A function f is called an antiderivative of f on the interval if f prime of x is equal to f of x for all x in that interval. I'm glad I wrote that down instead of just saying it. A function f is called an antiderivative of f on an interval if f prime of x is equal to f of x on x in that interval. The most general form of an antiderivative is f of x plus c plus some constant. Okay. The idea is that we have a function, and what you want to do is you want to find the antiderivative. You want to find the original function for what the function we have would be the derivative of. You're given f, you want to find the original function. You're given the derivative, you want to find the original that gave you that derivative. We add plus c in order to give us all the possible outcomes, all the possible antiderivatives. Because there is a constant. Because what is the derivative of the constant? It is 0. So if f of x is our derivative, there's that plus 0. There's that derivative of that constant. There could be some constant involved. Now, we will have ways of figuring out that constant. We will address that today. But you need to add that constant to it. Because every derivative, the derivative of x squared, the derivative of x squared plus 3, the derivative of x squared minus 5, are all the same. How do we know which one is which? We can't assume it's just x squared. There might be a plus or minus some number other than 0. That's why we add the plus c until we know for sure. Okay. Do not forget the plus c. You will lose points if you forget the plus c, plus some constant. It is an important one. The process of finding the antiderivative is, oh, lo and behold, anti-differentiation. Some basic formulas. Now, you'll notice the shirt that I'm wearing today are your rules of derivatives. You're just going backwards. Okay? If my function is a constant, the antiderivative is that constant times x. Because what's the derivative of 2x? 2. The derivative of negative 3x is 3. So the antiderivative of 2 would be 2x. Going backwards. Formulas are going backwards. When I told you that being really good at derivatives will be important second semester, when we're not actually taking derivatives anymore, this is what I was talking about. Because the better you are at derivatives, the easier antiderivatives are. When you're taking the derivative of a power, you bring the power down up in front, reduce the exponent by 1. You do the exact opposite. You increase the exponent by 1. And then you have to have 1 over what that exponent is out in front. When I take the derivative of x cubed, I don't get x squared, I get 3x cubed. So the antiderivative would have to have a 1/3 in front. The one time you need to be absolutely careful, and this is the one thing that screws everybody up, okay, is when I have x to the negative 1. X to the negative 1, you need to think about that as being 1 over x. If you have x to the first power in your denominator, the antiderivative of that is not x to the 0, because that's what it would be if you're adding 1 to the exponents. Right? If I have x to the 0 or x to the negative 1, and I use this formula here, and I add 1 to the exponent, To get the antiderivative, well, that would give me x to the 0, but x to the 0 is 1, because anything to the 0 power is 1, and the derivative of that would not be 1 over x. The derivative of that would be 0. The only time you have to do it, this is the one that screws people up more than anything else. When I have x to the first power in the denominator, or x to the negative 1, the antiderivative of that is the natural log. And this is, once again, if you know the rules, it's really not that difficult. If f of x is equal to e to the x, then the antiderivative is e to the x plus c. Gotta always have your plus c. If you have e to something times x, it's 1 over that something times x out front. Okay, we'll do some examples here. It will get more complicated than this as we go forth. We do not address the product rule. We do not address the quotient rule. You don't really have antiderivatives for those. Okay. We don't address the chain rule. You kind of have an antiderivative for the chain rule. We will get to that in the next chapter. And there are a couple of other methods we will learn for doing antiderivatives for complex, more complex functions. For the most part, it's remembering what function you're doing the antiderivative of. What did I do? What function do I take the derivative of to get x squared? Ooh, I take the derivative of x cubed. So I have to have something where when I take that derivative, I do it. This is also easy to check your homework. Take the derivative of your answer, see if you got the original problem. If you don't, you messed up somewhere. Okay. Now, the antiderivative of a constant times a function is that constant times the antiderivative. So if I have the antiderivative of 3x squared, that's 3 times the antiderivative of x squared. Makes it easy to kind of do the antiderivatives. The constant out in front of your function, just multiply that times your answer. Concentrate on the variable portion. Ignore the constant out in front at first. So let's do some examples. Okay. If f of x is equal to x to the 7th power, the antiderivative, f of x, would be x to the 8th, because you increase the power by 1. Because when you take the derivative, when you decrease the power by 1 to take the derivative, to do the antiderivative, you increase the power by 1. Now, when I take the derivative of x to the 8th, and this is kind of the thought process you have to understand. When I take the derivative of x to the 8th, what do? I bring the power down out front. Do I have an 8 in front of the x to the 7th? No. So that means I have to have a 1/8 here. Because when I take the derivative of x to the 8th, check my work, you reduce the power, bring the power down in front, reduce it by 1. I don't have a 7, I don't have an 8 x to the 7th. I just have x to the 7th. I need the 1 over 8 to counterbalance bringing this 8 in front when I take the derivative. And then I always have to have a plus c. Second one, same idea. Do them one at a time. The antiderivative of 4x squared. Well, that would be x cubed. Increase the power by 1. Then I'd have to have a 1/3 in front to counterbalance this, and I've got the 4 here. So what I'd have to have is 4/3 x cubed. That's the antiderivative of 4x squared. Minus x squared, increase the power by 1. But I don't need anything in front because I do have a minus 2x. That's nice, no fraction out in front. Plus 5x, a constant by itself, is that constant times x, plus c. Okay, so questions so far? Do you understand where the coefficients on my antiderivatives are coming from? Because that is the most difficult part. Why do I have a 1/8? Why do I have 4/3? Why do I not have something in front of the x squared? That's the part that's probably the most difficult to get when you're doing the antiderivatives. Dealing with the exponents, that's not a big deal. You add 1 to the exponent. But what do I have to have that out in front? What's the deal with the one number out in front? I have to have the 1/8 here because when I take the derivative, what do? I bring the power down out in front and reduce it by 1. I don't have an 8 here, so I have to have the 1/8 to cancel it. Same thing here with the 4/3. To take the derivative, I bring the 3 down in front. Well, 3 times 4/3, that gives me my 4. Right. This one, you can't do derivatives with square roots as square roots or cube roots or fourth roots. What do you have to do? You have to rewrite it as a fractional exponent. You must do the same thing to do antiderivatives. Rewrite them as fractional exponents before you do the antiderivative. So your first step is to actually rewrite the function. So I have 4 times x to the 1/3 minus 3 x to the 5/2. If you can't take the derivative of something in that form, you can't take the antiderivative of something in that form. You must rewrite it to get rid of the radical, exponential form. And then I take my antiderivative. So 1/3 plus 1 would be 4/3. Right? Not 2/3, 4/3. Remember how to add your fractions. Now, what do I need out in front? When I take the derivative of this, I bring 4/3 down in front. What do I actually need? I need a 3 here. 3 times 4/3 will give me my 4. There is an alternative way of thinking about how to set this up. It's actually pretty easy. What you do is you put the constant that's already there, take the antiderivative, x to the 4/3, and then what do I have to have out in front? 3/4, or my anti of that would be 3/4. Take whatever this is, flip it over out in front. It'd be 1 over that power. So I have 1/8. That's where the 1/8 came from. So when I have a fraction, I have 1 over 4/3. What's 1 over 4/3? 3/4. Okay. Simplify this for the next step. So my answer would be f of x would be 4 times 3/4, 3x to the 4/3. If nothing else, you can just put the constant out in front, take the antiderivative, and multiply the constant times the coefficient for your antiderivative. So I would have minus 3, and then I would have to deal with the antiderivative of x to the 5/2, which would be 7/2 for my new power. And then I'd have to have 2/7 for that out in front, 1 over whatever that exponent is. 1 over 7/2 is 2/7. Multiply these two together, minus 6/7 x to the 7/2. And then what else do I have to have? Let's see. I always have to have that plus c, with one exception. We'll talk about that later. And these are general antiderivatives. It could be 3x to the 4/3 minus 6/7 x to the 7/2 plus 1. My antiderivative could be 3x to the 4/3 minus 6/7 x to the 7/2 minus 92. I don't know. I don't know what my constant is. My constant could be 0. I have to give all possible antiderivatives. That plus c gives me every single possible one. Because the derivative of a constant would be 0. Whatever that plus c is will disappear. I don't know what that is. I just know that there's a constant there. And that constant could be 0. I just don't know yet. Okay. F of x equals 2 sine x. Good. So I'm going to have 2, my constant, times, what is the antiderivative of the sign? Negative cosine. Watch your negatives and positives. Plus c. The derivative of the cosine is negative sine. So I don't have a negative in front of the sign. I have to have a negative in front of my antiderivative. Watch your negatives and positives. Okay, if it was the cosine, it would just be sine, but it's the sine. Watch your negatives and positives. This is another one where knowing your rules is going to be important. What's the antiderivative of the secant squared? You're going to need to know what that is. And if you know the rules that the derivative of the tangent is the secant squared, you'll be right.
Why is it cosine squared?
It's not cosine squared, it's 2 sine, 2 cosine.
Well,
Because I have the constant 2 out in front. So if I have this is a constant times some function, my antiderivative is that constant times the antiderivative of that function. I can always pull that constant out. I'm going to tell you, that's going to be really, really, really nice later on. Being able to pull that constant out and deal with the function on its own, and then just slap the constant back in there when you're done. It's a really nice thing to be able to do. You can make some complicated things. Because if this was 3,492,000, you just pull the 300 million, you pull it out front. Get rid of it. Ignore it while you're doing the antiderivative. You can do that. Okay. Next one. Can't do it as it stands. Probably. I know I wouldn't even want to try. Looks like a quotient. I don't want to use a quotient rule. I have x squared. Ooh, that means I could do one with my denominator of x. But then you got to figure out what the numerator would be. Trying to do the antiderivative, split this up into a couple of things. Oh, no, you don't want to even think about the quotient rule in doing antiderivatives. That. Rewrite the problem. It's each one of these individual terms divided by x squared. That's it. And if you do that, do that first, and then simplify each one of those individual terms, then take the antiderivatives. Finish it. Okay, so your first step is to rewrite the problem. Simplify each one. First one you get x, second one you get 3, next one you get 4 over x. Notice I didn't write 4x to the negative 1. Okay. Minus x to the negative 2. There's a reason I wrote those last two the way I wrote them. Now, doing the antiderivatives. The antiderivative of x would be 1/2 x squared. Increase the power by 1. I don't have a coefficient in front. It's really easy. My antiderivative is easy. The antiderivative of 3 is 3x. The next one would be minus 4 over x. When I have 1 over x, the antiderivative of 1 over x is the natural log of x. I have 4 over that, which means I have 4 natural log of x. Now, and technically, your antiderivative has to be absolute value. Because I don't know what I'm dealing with here on x, and I cannot take the natural log of a negative number. Nor can you take the natural log of 0. Because e times itself will never be 0 or negative. No matter how many times you do it, that's what the natural log says. How many times, what power e gives me that number. Okay. And then this one, I have this one because it's not negative 1, because it's not just 1 in the exponent. If I had this one written as 1 over x squared, that's fine, but it is not the natural log of 1 over x. Just because it's the denominator does not mean your antiderivative is the natural log. The only time that happens is when I have x to the first power. Something in the first power is a natural log. If it's not the first power, that's why I wrote this as a negative exponent. Because here I do, add 1 to your exponents. And then what do I have to have out in front? I have to have a 1/2. And technically, I have to have a negative 1/2 out in front. Okay. Or actually, no, sorry, I was thinking this one. My bad. I do not have to have the 1/2. I do, however, have to have a negative. Take the derivative of this. What do? Bring the negative 1 out in front. Decrease the power by 1. That'll give me what I got here. Plus c. Most common errors come from the antiderivatives of where you have variables in the denominator. If it's x to the first, your antiderivative is the natural log. If it's x to any other power, rewrite it as a negative exponent and use the power rule. Okay. Now I do have one more example for you. It's not on here, but I need to add this in here. Okay, let me explain. So this, I'm giving you a function, and I want to find the specific function, the specific antiderivative that passes through a particular point. Okay. On the homework I'm going to give you, and I'm not using the book because the book doesn't have nearly enough practice problems for this by any stretch of any imagination. I only got maybe 7 or 8 problems to practice this. That is not enough. It isn't. It's not nearly enough. The one I'm going to give you has it written like this. And what that means is that point is an element of the antiderivative function. In other words, I want the antiderivative that passes through that point, through the point 2, -2. This is where the ones where you will not have a plus c when you're finished. You will have a plus c in your process, but we will find out what that C is and find the specific antiderivative that passes through that point. So my first step is to take the antiderivative. That would be x squared minus 5x plus c. But then I plug in negative 2 for x and f of x and solve for c. So what I want to do here is I want to know the specific one. So I take this xy coordinate and I plug it into my antiderivative, solve for c. So I'm going to have negative 2 equals 2 squared minus 5 times 2 plus c and solve for c. So that's negative 2 equals 4 minus 10, negative 6 plus c. Add 6 to each side. So I get c equals 4. Right? So my actual final answer would be f of x squared minus 5x plus 4. The specific one that it goes through. That's what that one's about. We will be doing a lot of stuff with antiderivatives as we work through this chapter and the next chapter and some of the chapter after that. Okay, it'll be a big deal. The plus C will be a big deal. I am thinking off the top of my head about a particular AP question where you have to find the antiderivative. You're solving integration, you're finding antiderivatives, and it'll be worth 5 points for the one solving for the original function. Generally speaking, about 4 or 5 points, usually about 5 points. One of those points is the plus C. You don't have the plus C, you miss a point. But here's the other thing: 5-point problem, but you forget the plus C, they actually will have a note on the side. Maximum 2 points, no constant. You forget to put plus C, the most you can get is 2 out of the 5 points. You forget the plus C, you're done. Doesn't matter what the rest of the problem is. The best you could do would be 2 out of 5. And they have that. We'll see those notes because you will be doing them and grading them yourself, and you will see what their grading is. Okay? It's an important part of the problem. When you take your testing here, you don't have plus C, you're losing points. Now, it is one of those things where I am often